Hello and welcome to lesson 5.4 on proving triangles congruent using the angle side angle and the angle side criteria. Okay, so these are two different criteria. So criteria just kind of means like, I guess you could say rules or requirements. There are two different kind of ways that we're going to look at triangles and prove whether or not two triangles are congruent to each other. Okay, so the first principle we're going to look at is the angle side angle principle. So let's read this real quick and see kind of how they describe it, and then I'll describe it in my own words. Okay, so first they give us a vocabulary term called an included side. This is the side of the triangle between two angles. So if we picked angle E and angle D, the included side would be the line segment ED. Okay, so it's the line segment that's between two angles that we're thinking about. So if you pick any two angles in a triangle, there will be an included side that includes both of those angles. If two triangles are formed using the same two angle measures and included side length, then there's a series of rigid motions that will show that the two triangles are congruent. This leads to the postulate below. If two angles and the included side of one triangle are congruent to two angles and the included side of the other triangle, then the triangles themselves are congruent. Okay, so let me give an example of that. So if we looked at D and E and the included side, so kind of a pair of three objects, angle, side, and angle, if we can prove that that is congruent to angle, side, angle over here, then we know that the two triangles are congruent. We'll be able to kind of infer that the third angles are the same and that the other side lengths are all the same. Okay, and that's what we need to prove a triangle is congruent to another. We need to prove that all three sides are congruent and all three angles are congruent. So this ASA idea, angle side angle, is saying that all you really need to show, the minimum that you need to show that allows you to just kind of show that everything else is true also, is that two angles and the side between those angles need to match up with the other triangle. Okay, so let's look at why that's true. If I show you these pictures right here, these are two congruent triangles. They are, if we rotate them, they may not be overlapping, but we can make them overlap. I can set one on top of the other, and you get congruency. Now, let's look at this triangle that I've kind of cut into pieces real quick. The angle side angle theorem would only deal with two pieces at a time. So by which I mean, like, you could have these two angles and the included side between them. These sides are kind of undefined. They're not ending when I just have these two pieces. So right now I say that these two angles exist and this length between them. I could also do these two angles and the length in between them, or these two angles and the length in between them. As long as I know one of those sets of things, an angle, a side, and an angle, okay, I can work with that. So let's see why I can work with that. Okay, once you have two angles, you know for a fact the third angle, because the three angles always add up to 180. So there's not like a big range of different possibilities. You just need to have that third angle that makes it all add up to 180. There's only one choice. So first of all, if you know two angles, you automatically know the third angle. Now, you could say that, well, we could have two angles and we could change how far apart they are, right? We could have them maximally far apart. We could have them fairly close together. And in both of those situations, I could slide in that third angle, right? So I could make a triangle where it was rather small, or make a triangle where it is, kind of medium size. And either of those triangles work. Okay, so those triangles, those both had those three angles in them. So those angles didn't change, right? The physical piece of paper that I drew on, I didn't change the drawing. So those angles are the same size no matter where I put them. Okay, but here's a different idea though. Once you've decided how long that included length is going to be, how long this side is going to be, so let's start here. There is only one spot that I can put this. There's only one triangle I can make. So I can't, for example, say that, this top line is going to be a little shorter, because then these ones don't line up. These angles are fixed. So there's only really one position that gets all of my dotted lines to line up. Okay, so let me repeat the point there. when I have angle, side angle, when that is defined, when I know what my angle is, I know what my other angle is, and I know what the side length in between is, that only leaves me with one spot that I can put this. That only leaves me with one possible triangle I can make. Okay, so basically what that's saying is as soon as you know this side here, if you already knew the angles, you automatically know the other two side lengths. Okay, so let's make the shorter one again. So if I know the angle, the side, and the angle along the bottom, angle, side, angle, then I know for a fact how big the other sides must be, because there's only one place that that third angle could go. So the other sides need to be, this big and that big. Okay, so that is sort of the main idea with angle, side, angle. As long as you know angle, side, angle, you automatically know the third angle because they need to add up to 180. And based off the length of that side, whether it's a short side, a medium side, or a long side, the length of that side will automatically tell you how long the other lengths need to be. Now, it won't tell you the number. That's something you'd have to go through and solve for. But it tells you that there is only one possible triangle you could make that has that angle, side, angle. Once you've decided the angle, side, angle, you have a triangle. Okay, so now the very last thing that we want to say is that once you have your angle, side, angle, and you know that that angle, side, angle kind of trio defines a certain triangle and it defines no other triangles, just this one, then you would also know that if all of the information you had was that the angle, side, angle matched another triangle's angle, side, angle, if you knew they matched, if you didn't know anything about the third angle or the other sides, if you just knew that that angle, side, angle trio matched, well, then you would know for certain that those triangles were congruent. Because once you've defined an angle, side, angle trio, once you've defined those three things, you are stuck with one and only one triangle. Okay, so if this one is stuck with one and only one triangle, and this one can only be this particular triangle because the angles and the side are defined, then you would know that these two triangles are congruent. So basically, we don't need to show that every angle is congruent to every other angle. We don't need to show that every side is congruent to every other side. Once we've shown that there's an angle, side, angle trio that matches another angle, side, angle trio, then the rest of it just kind of falls into place. The rest of it, as in the final angle, falls into place. We know what that is because they have to add up to 180. And the other two side lengths fall into place because we know that they need to be the appropriate length that gets all of my sides to match up at the vertexes. Okay, so that's kind of the main principle, and we will move forward looking at some concrete examples of working with that in the next video.